So what we know from before is that in group theory we usually used to write a group which is nothing but a set of elements, and it contains identity and some other group elements, their inverses, and this set it follows some specific rules. Now what we did, we said that these elements are nothing but operators that operate on coordinates. So let me remind you that once we were talking about a group that contained two elements, E which was identity and I which was inversion. So when inversion was acting on coordinate x, we used to get minus x, and when E used to act on x, we get the same element x. So the whole idea is that the elements of the group, they act on coordinates, and then we said that based on these elements we created operators corresponding to each element, and these operators, they acted on functions psi of x or whatever, and then we created a space of functions. So consider I have a space of two functions, psi1 of x and psi2 of x. If you remember, we took one as an odd function and one as an even function, and then based on how, for example, OA acts on this basis, we created the matrix representation of the operator OA, which was represented by DOA. So it's a matrix. It's a matrix representation of the operator OA. So this was what we did before. So the group elements acts on coordinates. Using the group elements, we took operators that acted on functions. These functions are basis functions, and using these basis functions you can span a vector space, but that's another story. Depending on how these operators act on the basis function, we developed a matrix representation of the group elements. But now what if the group elements itself are the matrices? That's the point. So now we can have group elements. So we can have group elements, and I want to keep the idea that group elements, they act on coordinates. So what if we can we can have group elements that act that are themselves matrices. So they are themselves matrices, and again they act on coordinates. So this is the idea that we will follow. This kind of group are called as, they have a special name called as a matrix group. So matrix group is, for example, so consider now you have a matrix group G that contains an identity matrix which is 1 0 0 1. So I'm talking about 2 cross 2 matrices set, and there are other set of elements which are matrices dot 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 dot. So we have some finite set of matrices in a group, and all these matrices are 2 cross 2, and the components of the matrices are real. For example, 1 0 0 1, they all belong to the real number. Then I can give a special notation to such kind of group. So this is G L. I write 2 because it's a 2 cross 2 matrix, and I write R because all the components of the matrix are from the set of real numbers. So in case I have G which contained the identity as usual 1 0 0 1, but it contained elements which had I in it. Apart from real number, we have some complex number, and we have a group. Then we say that such kind of group, they have a special name called as GL, since we are talking about 2 cross 2 group, and now the components, they belong to the complex number, so I write C. That's it. That's the simple idea. So the whole idea is that we can have groups whose elements are themselves matrices. What more? Well, next question is, can we have, so as you see in the previous one here, that I'm saying that the matrices, so there are matrices, first matrix, second matrix, third matrix, and the matrix are such that maybe they are finite. But now if I ask you, can I have a group of matrices, but the group should contain infinite amount of matrices? Now you would say, how can I construct say a 2 cross 2 matrix group that contains infinite amount of matrices? Well, let me give an idea. How about all the group elements, they have this particular structure. So we have this cos theta here, and we have this minus sine theta here, and then we have this sine theta here, and then we have cos theta here. So this is a general representation of all the elements which is inside G. This is not one matrix. And why I'm saying that this group is a group that contains almost infinite amount of elements, and it is a continuous group, because your theta which ranges from 0 to 2 pi can take any value from 0 to 2 pi. So since theta ranges not in a discrete manner, you can take any value, and for every theta you can have a matrix. So this G, now this new definition of our group, I mean the new group G, contains not only infinite amount of matrices, but the matrices are continuous. You cannot say this is the first matrix and this is the second matrix, because between the first and the second matrix, depending upon theta, you can insert one more matrix. So you cannot talk about discrete matrices. Okay, so this is an example of what is called as continuous group. So apart from group that contains matrices, we can have group that contains matrices, and the matrices are continuous. So this is just an example of what is called as continuous group. Now you might have in your mind that, okay, what about Lie groups? Well, Lie groups are continuous group, but with a special property. You cannot say that just any continuous group is going to be a Lie group. Okay, so this is an example of a continuous group, and I hope you understand that this G here contains matrices, and they are all continuous. So you have a continuous distribution of matrices, or whatever it can be said. I don't know if the sentence is correct, but this is it.
Sir, can we have a such group which has infinite number of elements but it is discrete?
I don't know yet. I have to find it out, and I'll let you know in the next lecture. Okay. So okay. Right now we have infinite number of elements and we have continuous matrices. Okay, can you guess what will be the for example, let us take G. Can you guess for what value of theta you can have an identity matrix, because we know that every group must have identity matrix. So of course, for theta equals to 0, you get the matrix 1 0 0 1. You get the identity matrix. Similarly, for some other value of theta, you will have some other matrix, and it's the infinite amount of matrices depending upon how you choose your theta. Well, this matrix is something that we have seen in our day-to-day physics life. Let me remind you that again we come to the idea that our group elements act on coordinates, and this matrix looks something that we already know. So let me remind you that consider you have this x and y, and consider you have a vector. So in the xy basis, so this is the vector, and say this point is x comma y, and then all of a sudden what you do is you rotate the matrix, you rotate the basis state to new points. This is x prime and y prime. So now you have new basis, and the rotation happens by some angle theta. Then in this new basis, this point will have coordinates x prime and y prime, of course, and we know how these are related. So x prime and y prime is related to x and y through this matrix, and it has a name. It's the rotation matrix in 2D. So cos theta minus sin theta, cos theta, and x and y. So again, I verified that, look, my matrices, they really act on coordinates. Now the coordinates are in 2 dimensions. So before that, when we talked about I acting on x and giving you minus x, it was happening in 1D, but now things are happening in 2D. Okay, so now question is, I can give them a special name. How about writing r of theta? That means my group G, so this G is this G, I can simplify the way I write it. So my group G contains all the matrices r of theta, where theta belongs from, say, 0 to 2 pi. So if I write in this shortcut notation, this is also informing you that, hey, look, I have a set, and this set contains lots and lots of matrices depending upon the parameter theta. Depending upon the theta. Now question is, okay, we have the set, but is it really a group? So is it really a group? Does it satisfy the axioms of being a group? That we have to check now. So let's give a quick check. So whether it's a group or not, let's see. So first is, we know that if r of theta belongs to the group G and r of phi belongs to the group G, then if I multiply them, I should get some r of alpha, and this also belongs to the group G. And what should be the structure of r of alpha? Now r of alpha should have the same structure as r theta and r phi is, which is cos alpha minus sin alpha, and then sin alpha, and then cos alpha. The question is it possible? So what you do is, you do the mathematics. We'll not do it. I'll give you short way of. So you have r theta, and you are going to multiply with r of phi. What are the matrices? So for r theta, you have cos theta minus sin theta, and again the sin theta and the cos theta here, and then it gets multiplied with cos phi minus sin phi, and then we have sin phi and cos phi. Well, when you multiply them, to your amazement, you will find that this actually gives another matrix that actually belongs to the group G, and now it is, this alpha is nothing but theta plus phi. So you're going to get this sin theta plus phi. So if you look at the structure of the result that you get, the result is nothing but an also element of G. It is straightforward. Okay. So one object is proved that, okay, so if I take two objects or two group elements from G, and if I multiply them, I get G. Now question is, do we have an inverse? Yes, I just showed you that we do have an inverse, and the inverse matrix is when your R takes theta equals to 0. So if you plug it in, you'll get 1 0 0 1. Then the question is, does it have inverse? And you can also find the inverse of each of the matrices, such that when you multiply R inverse with R, now you should get identity, right? So you can give a quick check whether this exists or not. So thus we have a group of rotation matrices, so group of all rotations. But now the interesting thing comes that although I have a group of rotations and it looks like this, is it possible that I can make a transformation? Remember the transformation such that it is reducible and something like that. So can I have transformations that will reduce this matrices to maybe diagonal form? That will be very nice. So the whole idea is, can I have a matrix V? Of course this matrix is going to be 2 cross 2, and this matrix is such that when I apply in this way to any element of group rotation group G, I get new elements, and these new elements, they form a group, they form a set, and the set forms a group. And can this new element be diagonal? By diagonal I mean you can have elements here, you can have elements here, but here you'll have 0. Okay, so that's the whole idea. And if it happens, then I can say that the matrices are the elements of the rotation group, which are 2 cross 2 matrices here, they can be diagonalized. Okay, so it turns out we do have V, and I'll tell you how to find V, but let me tell you that there exists V. So there exists V such that when you apply this and this 2 cross 2 matrix here, and you are going to apply it to our matrix cos theta minus sin theta cos theta, and then you have your matrix V inverse here, and it really gets diagonalized, and it's very interesting. You get e to the power minus I theta 0 0 and e to the power I theta. That looks beautiful.